So, good afternoon, everybody, and thank you for the invitation to participate in this event. Today, I'm going to talk about the role of additive manufacturing and rehabilitation and for persons with disabilities. My name is Ola Harrysson, and I'm a professor in industrial and systems engineering, and I'm also the director of Center for Additive Manufacturing and Logistics at North Carolina State University. So why are we want to use additive manufacturing in these applications? Well, there are many of the off-the-shelf devices that exist. They have limited adjustability and they come in limited sizes. So in many cases, it is very hard to get a good fit for the majority of the patients because we're all different. And there are many assistive devices that needs to be personalized or customized or both because you need a perfect fit to the anatomy for the device itself to work properly. One particular is with children. They grow fast and they need updated devices on a regular basis. And of course, their anatomy is constantly changing as well. And the idea is that you want to fulfill all the needs of the users for a particular device that is going to help them. This could be potentially customized grippers for prosthetic hands, for instance. We've done some work where you took a prosthetic hand device and then customized it so that the person could do specific tasks that they needed to do either for work or for some activity that they want to participate in. So these could be for sports or they could be for work or whatever it is that they want to be able to do. So I'm going to show you a couple of different areas where 3D printing has been used quite a bit already. And one is 3D printed braces. And this could be for temporary use for recovery from an injury, or it could be for permanent use for somebody with a disability. When we're designing these custom devices, we can either use medical imaging like CT scans or MRI scans, or we can use a surface scanner, which is either based on a laser or light white. Because in many cases, all we really care about here is what's on the outside, what's the contour of the skin, where we're going to place this device. So with this, we can optimize the fit, but we can also optimize the strength. So in these cases, it is very easy to change the thickness. For instance, so you make it stronger and stiffer in certain areas, and you make it softer and more flexible in other areas. And you can get then different functionalities. And in many cases, these are more comfortable than traditional braces. What is very popular is to make these into a mesh type of structure, so it'll breathe, and you won't get as sweaty with these as you would do with traditional braces that are completely covered. Also, it's easy to redesign and print as needed. So in many cases, as I said, children are growing. They might need this for several years, but they need to get those changed. And you might also have different needs if it is for recovery. Maybe you want something that is more restricted and stiffer to protect the limb or whatever it is after the injury. But as you're going through the recovery, you might need that to change to be more flexible and give you maybe more range of motion. And those can easily be done by very, very quickly redesigning and printing these devices. And also, of course, you might have a change in the anatomy as you're going through these treatments. So this is a case when you're treating scoliosis. So these 3D printed braces, they need to change as the curvature of the spine is being corrected. Also, aids for specific tasks. So this is something that is becoming more and more popular. And we know that many individuals with some sort of a disability have issues with everyday tasks. And this could be due to stroke, this could be due to arthritis, maybe it's an accident, or a congenital thing that is going to last for a lifetime. And there are some of these help devices out there, but they're not customized for each patient. And again, there might be a few different sizes, but it's not going to fit perfectly for every patient. And also, with the patients themselves have different needs. If you have two stroke patients, what they can and can't do can be very, very different. And also what they need to do can be very, very different. And of course, we're all slightly different when it comes to size and anatomy. And so these have become very popular things to work on. And as you can see here, the bottom here, these are devices where you have the orange piece here has been designed for this particular patient. And then they have all these different attachments that help them with some of these daily activities. So custom devices just makes life easier. Also, another area where this has been going on for a while is within 3D printed prosthetics. So if you have a traditional prosthetic using a socket, they are normally handmade. It takes about 6 to 8 weeks to make a socket, whether it's for a limb or an arm. And sometimes even after that, and during that period of time, the patient has to come back several times to do fitting of that socket. And then they make adjustments, they have to come back again. So it's a lengthy process. And sometimes they still don't get a good fit. And so if you're unlucky and you get a prosthetic that doesn't fit you very well, they're usually only replaced once a year. So now you have to live with the idea that your socket is not going to be very good for an entire year. So when we're looking at 3D printed sockets, they're faster to design and produce because we're basing this off of a surface scan of the residual limb. And using special software, we can then design these sockets directly in the computer. And then it's just a matter of them printing out the different components. So in this case, we're not just printing the sockets themselves, as you can see. We can also then personalize these to have a specific look. So we can actually print the entire prosthetic, not just the socket itself, and then putting in the components that are needed to get a strong computerized knee, for instance, or an ankle. And so with this, since it is faster and in many cases is actually cheaper than doing it the traditional way, and they usually get a better fit for these patients. And again, it's all about customizing and personalizing these. So we're not putting these designs on there to try to hide that it is a prosthetic, but it's trying to bring out the personality of the person that wears it. And so these designs are often discussed with the designer, and it's the user that decide what they want it to look like. Here is a project that I was involved with. We teach a course here at NC State that is a multidisciplinary product development course for grad students. So we have engineering students, we have industrial design students, and we have business students, MBA students. And during a semester, we put together these multidisciplinary teams, and they develop a product. And in this case, this project was sponsored by a nonprofit organization called Life Enable. They're a group of prosthetists that are basically collecting old prosthetics, and then they're going to developing countries to refit these prosthetics for people that need them. And they usually go a couple of times a year to places like Guatemala. But the problem is that sometimes they can't get them to fit very well, and they can only do so many patients in a 2-week period. So one of the people behind Life Enable had this idea of what if we could make an adjustable prosthetic, and that way they don't need to go down there and fit them, then the patients will be able to fit them themselves. But it had to be a low-cost version, but it still needed to be fully functional. So this group that eventually named their company OpenGate, they started working on an adjustable socket for above-the-knee amputations. And in developing countries, it's very common that they always do above-the-knee amputation, regardless on if it is just a foot. And it's just to prevent from having to go back and doing more amputations later. So there were a couple of different parts to this. One was the adjustable socket, then it was a good functional mechanical knee joint, and also a flexible foot that didn't need a joint that would still be functional. And as I said, these were really meant for third world countries so that we can make these and ship them and you don't need a prosthetist to really do the fitting of these prosthetics. Now, it turns out that one issue with the traditional socket prosthetic is that the soft tissue in the limbs change throughout the day in volume and shape. So you might have a socket that fits very well in the morning, but towards the afternoon, you don't have such a good fit anymore. So the idea was also to be able to provide these adjustable sockets to people here in developing countries. And they would then be able to use these when their traditional socket is not fitting very well. And of course, a traditional prosthetic with a computerized knee, maybe a computerized ankle joints, they're running anywhere in the $70,000, $80,000 range. So obviously, you don't want to take one of those to the beach. So the other idea is to have a stable, fully mechanical prosthetic that they can use with activities where their regular prosthetic is not going to fit. So in this case, they're using a mix of 3D printed components as well as traditional manufactured parts. After the course ended, there were 3 students in that group that decided to take this to the next step. And they started their own company. As I said, they named it Open Gate. And they started raising funding. So they've raised over $50,000 so far. And these 3 students are now all about to graduate, and they have decided to do this full time. So I really hope that they will be successful. They have already tested this. They've been down to Guatemala. They have tested it on patients down there and got some feedback, and it looks really promising. Right now, they're just working out some design details for the production of this. We've also been involved in custom implants. So in many cases, if you have an unusual anatomy, or it could be that you have had an injury, you won't be able to find an implant that is going to fit for you, that is an off-the-shelf implant. So here at NC State, we have a very good vet school. So we've been doing work with them, but what I'm showing here can also be done with human patients. So in this case, we had a large cat that came in at about 28 pounds and had osteosarcoma, and it was treated with radiation therapy, and they cured the cancer, but it destroyed the bone in the knee region. So this big cat needed a total knee implant. So the problem is that there are no knee implants for cats. So we put together a team here at NC State. We designed these, and because of the poor bone quality in the knee region, we needed to have fairly long stems in both directions to be able to anchor them to bone further away that had good bone quality. So these were all designed, and they were then fabricated by EUS using cobalt chromium. So they have a 3D printing process that is laser-based. And we also designed in bone ingrowth surfaces into this, so that hopefully to get bone ingrowth, to get a fixation for the life of the patient. So here's some pictures from the surgery. So as you can see here, because of your putting these stems in, to be able to use the screws that will secure it in place before we get the bone ingrowth, you also need custom cutting and drill guides. And so they were designed at the same time, and they were also being 3D printed out of a polymer. And here you can see the results. So this is the knee implant in place in the patient. And then we followed up by using a force plate. So this patient came back on a regular basis. And the lower line here, you can see that's the reaction forces from the leg that has the knee implant. And so obviously it's putting less weight on that particular leg. But for every time it came back, this line was getting closer and closer to the other lines here, which means that he's putting more and more weight on it, and also means that the pain level is going down. Another case that we had, where it was a large breed dog, also with osteosarcoma in the proximal portion of the tibia. And in normal cases, they will amputate the leg in that area. The issue here was that it was a very large dog, and the owners were not sure if it would be able to ambulate on 3 legs, so they wanted to look for a different solution. So we started out with designing what is called a limb-sparing implant. And you're basically creating an implant that is going to replace the section of the bone that has to be removed. We were using medical imaging. We were looking at where we were going to remove the bone, and then using the exact same anatomy for our implant. And as you can see here, so the yellow part is really the original the geometry or anatomy of the bone. We also had sections here, what is seen in gray. Those are mesh structures. So again, we wanted to get the bone to grow into this area. Since we're removing one side of the knee joint, we actually have to put in a knee implant. So this is an off-the-shelf knee implant that exists for dog that we then combined with our custom designed limb-sparing implant. And since you're removing such a large portion here of the bone, you have all your insertion points for your ligaments and tendons. And to get a fully functional knee joint, we had to create insertion points so that we could reattach all the ligaments and tendons to the implant itself. So this time it was fabricated with an Electron Beam Melting machine, which is also a metal 3D printer out of titanium. And then it was finished here in our facility. The surgery was about 8 hours, so it was a kind of a complicated surgery. But with this, we showed that we can have a custom implant that is combined with the traditional knee implants to get a fully functional limb. Osteosarcoma is something that is common both in humans and in animals. So here, we've continued to working on this idea that creating these limb-sparing implants that works better than what we have today. So on the bottom here, you can see this is normally what happens if you have osteosarcoma. Let's say it's in our forelimb, you will go in and cut out the section that is affected. That section gets replaced by a steel rod, and then you use a bone plate to attach to the steel rod, and then you connect it to the 2 other sides. And this kind of works, but not very well. And the reason for that is that this construct here is much, much stiffer than the bone itself, and eventually is usually leading to loosening of these implants, and they still have to go in then and complete the amputation. So our area here is that we replacing that section that we're cutting out with the same anatomy or the same geometry, but using these mesh structures that we can design to get specific stiffness so that we can match the stiffness of the bone, so they will behave more like the natural bone. And then the plates and the ends here we're attaching to the other sides of the limbs can be customized, and that way it will get a better fit, and these limb-sparing implants will hopefully last longer and work better for the patient. Another area that we've been working on is something that's called Transdermal Osseointegrated Prosthetics. And so if you don't have a socket to attach your prosthetic limb to, you can do it with an implant. And this was something that was developed by Per-Ingvar Brånemark and Rickard Brånemark in Sweden back in the 80s. And we've been doing a number of patients from the vet school here, but they are still doing the same thing for human patients. And so we've been through a number of design iterations, and this is the most recent design that we have. So the implant itself gets designed to fit to that particular patient. Then we have this mesh, or the basket as we call it, towards the bottom. And the idea here, if we're looking at during surgery, is that a soft tissue goes on the inside of the basket, the skin gets stretched on the outside, and then suture through these openings here to keep it all together. And here you can see after the surgery, so there's only a small piece of this implant that sticks out through the skin. And after a couple of months, we've got full healing here. The skin has attached to the titanium surface, so there is no fluid coming out, and then you can have any bacteria going in either. Then you can have different prosthetics that you're attaching to that piece that is coming out through the skin. So the first prosthetic paw that we made was also 3D printed out of a rubber material. And it worked well, except for when you're walking outside on pavements, it will wear it down very, very quickly. And so we found a solution to that, used a tennis ball at the end of that prosthetic paw, and it actually works very, very well for the patient. So over the years, we've done a number of these. Sometimes we've had numerous cases going on at the same time. So some of these components have been customized or standardized and comes in different sizes. So depending on the size of the patient, that just makes it easier to produce. But then the implants themselves, what is going to fit to that bone, is all going to be custom. And again, they're all 3D printed out of titanium. So Jack here was the first patient that we ever did that had a bilateral amputation on his back legs, and obviously had a very, very hard time of ambulating. So we decided to do both at the same time. And here you can see the custom implants that have been fitted to 3D printed replicas of the bone itself. And here you can see right after surgery what it looks like. And then, of course, we let it heal for about 4 to 6 weeks before we put the prosthetic feet in. And Jack went from not being able to ambulate at all to be able to run and jump and enjoy life. So I thank you very much for your attention. And if you have any questions about this, please feel free to contact me. And here you have my email address. And there's also the web page for the Center for Additive Manufacturing and Logistics. Thank you very much.